Hi. Today we shall be developing a regression model that we shall be developing today. And here we have three variables. One is sales, and the second one is price of the product. Okay, first is sales volume, that is sales, right? And the second variable is the price of the product, and the third variable is cost for advertisement. We have these three variables, and here you can see sales is our dependent variable and price and ad are independent variable. Okay, so variables are here. You can see sales, price, and the cost of ad. We have these three variables, and our sample size is 30, right? The sample size is 30. So these are our variable, and these variables or the data is called, our data is a cross-sectional data, meaning that we have collected data at a particular time, such as suppose we have collected this data today, then we can call the data cross-sectional data. Or we have collected the data, suppose in a particular year, such as in the year 2011 we have collected data. So this type of data is called cross-sectional data. And what does mean by time series data? Time series data means we have collected data such as from 1980 to 1990. So this type of data is called time series data. But our data is a cross-sectional data. We have collected it, suppose today. Okay, now we shall be estimating our models, and so I go to analyze, I go to linear regression model, right? I choose it. Then sales is our dependent variable, I take it here, and price and ad are the independent variable, I take it here. Okay, so here what is our target? Our target is to check whether price and ad, these two variables, can influence our dependent variable or not. That we want to check today, whether price or ad are significant or not to influence our dependent variable, which is sales. Okay, now we also want to check whether the model is nicely fitted or not. We want to check whether our model has serial correlation or not. We also want to check whether our model has heteroscedasticity or not. We also check whether the residual is normally distributed or not. Okay, so we check one by one. How? I go to statistics to check it. Okay, here I choose estimate. That means all the coefficient of the independent variable will be estimated. And here I choose model fit, meaning that the value of r square can be estimated. And we also choose Durbin-Watson statistics. I choose it, and it is the residual, meaning that we want to check whether the residual of our model has serial correlation or not. And if the model has serial correlation, we cannot accept the model. Our model should be free from serial correlation. So that is why I choose Durbin-Watson statistics. Okay. So it is done. Then I check, I go continue. Okay, then I choose plot. Okay, here you can see plotting, linear regression plot. Okay, here y means y-axis and x means x-axis. Okay, here what I do, in the y-axis I bring z-recit. Z-recit I bring it here, and in the x-axis I bring z-pred. I bring it here. Okay, and here what does mean by z-recit? It means that standard residual of the model will be on the y-axis. That means plotting of the standard residual will be in the y-axis. And what is z-pred? Meaning that standard predicted value will be in the x-axis. So the predicted value, meaning that our cells, that is our dependent variable or predicted variable, right? So the predicted cells value would be in the x-axis and the residual will be in the y-axis. Okay, and we are doing it to check whether our residual has heteroscedasticity or not. And if our model has heteroscedasticity, we cannot accept the model because heteroscedasticity is not desirable. Okay, so this one is set. Then I go to continue. Okay, and finally we check our residual is normally distributed or not. So I go to save to check it, right? And it is the residuals, right? So here I choose standardized residuals, that I choose, right? Meaning that our standard residual is normally distributed or not. And if the standardized residual is not normally distributed, we should not accept the model. The residual should be normally distributed, and that is desirable. And actually this one means actually Z recit. That means normal distribution of the residual, or I can say standardized residual, right? This one is this one, right? That is called standardized residual. That is here. Okay, so everything is set. Now I go to continue. So our model is set for further checking, and here I choose enter. There are so many methods, right? Out of so many methods, I choose enter method. Enter method is the standard regression method, and where all the variables will be joining to estimating the model. Okay, then it is set. I click on the OK. So result is coming up gradually. You can see the result has come up. Okay, the result has come up. You can see from here. It is the result, right? Okay, so first I check our model summary. So first I make it big so that you can see better. I make it big. Cell properties, I choose 16, right? Then I press OK. I press OK. So it is the model summary, and here you can see our dependent variable is cells, and the predictor or independent variables are add and the price, right? These are two independent variable or predictor, right? Predictor. That means these two variable can predict cells. Okay, so first I talk about R square, meaning that whether the model is nicely fitted or not. Okay, what is the value of R square? The value of R square is 88%. What does it mean? It means that 88% variation or fluctuation in cells can be explained by our two independent variable such as add and price jointly, meaning that 88% the fluctuation of cells can be explained by our two independent variable jointly. Okay, I can explain it better. Okay, I can explain it better. Suppose we have three variables such as cells, that is dependent variable, then price and add, those are independent variable, and here our R square is actually 88%. meaning that 88% means, it means that 100% minus 88%, meaning that 12%, right? So here 100%, 88% is equal 12%. Okay, here what is happening? 100% fluctuation in cells. 100% fluctuation in cells, and out of 100% fluctuation in cells, price and add contribute 88%, and the rest 12% contribute other variables which are not included in our model. I can again say in this way, the R square is 88%, meaning that price and add, I'm sorry, R square 88%, meaning that 88% fluctuation in cells can be explained by price and add jointly, and the rest 12% fluctuation in cells can be explained by other variables which are not included in this model. Suppose I can talk about other variables such as income of the consumer, test of the consumer, and so on. So I can say now, suppose I can say now that 88% fluctuation of cells can be explained by price and add, and 12% fluctuation in cells can be explained by other variables which are not in this model, such as income, test, and so on. So that is the explanation of this R square. That means price and add really contributing in the fluctuation of cells, because price and add contribute 88% fluctuation in cells, meaning that our model is nicely fitted. Our model is nicely fitted. That means data is nicely fitted, so we can accept this model. Normally, what is the guideline? The guideline is, if the R square value is more than 60%, then normally we say the model is nicely fitted, and higher the R square value, better the fitted model. That is always guideline. Okay, so here our R square is very high, so we are happy about the model. Okay, then we check the second issue, whether our model has serial correlation or not. That we can check from Durbin-Watson statistics. The value is here, Durbin-Watson statistics. From here we can check whether the residual has serial correlation or not. And what is the guideline? We have a guideline. So Durbin-Watson value can be between 0 to 4. So that is the range. And the guideline is that if the Durbin-Watson value is close to 0, meaning that there is strong positive serial correlations. And if the Durbin-Watson value is close to 4, meaning that there is strong negative correlation, right? And negative correlation or positive correlation, none is desirable. And when the Durbin-Watson value is close to 2, meaning that there is no serial correlation. There is no serial correlation. So that is the, normally we say if the Durbin-Watson value is between 1.5 to 2.5, then we can say that there is no serial correlation. Okay, so that is the guideline. And how much is our Durbin-Watson value? Our value is actually, I can see from here, 0.839. That is our value, right? So 0.839, that is our value, and it is not within 1.5 to 2.5, meaning that our model is suffering from serial correlation, and that is not desirable. So we cannot accept this model because our model is suffering from serial correlation. Okay, this part we check. Now we check another issue, ANOVA. We can talk about ANOVA, analysis of variance. I make it big as before. I make it big, cell properties, make it 16, right? Okay. So it has become big. Here is the F statistics and the significant value. Okay, here what is the guideline? This significant value means probability value or p-value, and the guideline is if the significant value is less than 5%, then corresponding statistics should be significant. But if the significant value is more than 5%, then corresponding F statistics is not significant. And here our significant value or p-value is less than 5%, right? Almost 0%, meaning that F statistics is significant. Okay, and F statistics significant meaning that our two independent variable such as ad and price, they are jointly significant to explain our dependent variable, which is sales. So the whole thing I am telling again, when the F statistics is significant, meaning that our independent variable jointly can our two independent variable are jointly significant to explain our dependent variable, which is sales. And normally we say if the F statistics is significant, that is always desirable for a model. Okay, so we are happy about the model because F statistics is significant. Okay, then we check our next issue, the coefficient issue, right? Whether our variables are significant or not. So I make it big as before so that you can see better. Cell properties, I make it 16, right? I make it big like this. Okay, here we have two independent variable. One is price and ad, right? Two independent variable. And here we have unstandardized coefficient and standardized coefficient. But we shall be talking about this one, unstandardized coefficient, right? All the time. And here is these are the coefficient and these are the standard error and these are the t statistics. Okay. Okay, suppose how to get this value 14.094, how to get this t statistics. Okay, this one actually 328.40 divided by 23.3, you can get this t statistics. Okay, then how to get this t value minus 1.375? You can get this t statistics from estimated coefficient divided by standard error. You can get that t statistics all the time. That means estimated coefficient divided by standard error, we can get the t statistics. Okay, and this is the significant value or p value. We call it significant value or p value. Okay, normally t statistics and significant value has a opposite associationship, meaning that when the t value goes down, significant value goes up, or when the t value goes up, significant value goes down all the time. But make sure here the t value, here I consider here I consider uh, here I consider the value which has no sign. That means we ignored the sign, right? That means absolute value. So we should ignore the sign. Example here, so meaning that what is the guideline? When the absolute t value goes up, then significant value goes down, or when the absolute t value goes down, significant value goes up all the time. All the times it happens. All the times it happens. Okay, for example, here you can see, for example, here t value is very high, 14. That is why the significant value is very small. But here absolute t value is small, it is only 1.375, and that is why significant value has become high. So meaning that this column and this column has a opposite direction all the time. Okay, now from here I want to see one thing. Out of these two variables, which variable is significant? Okay, so first I see the price. Is this variable significant? Yes, because the p value or significant value is less than 5%. So the price is a significant variable to explain our dependent variable, which is sales. Okay, then I talk about the second independent variable, ad. Is the ad significant? The probability value is 18%, which is more than 5%, meaning that ad is not a significant variable to explain sales. Okay, so out of these two variables, one is significant, price is significant. Okay, and what is the guideline? The guideline is most of the independent variable should be significant to be a good regression model. And here out of two, price 1 is significant, meaning that at least 50% are significant. 50% of the variables are significant, so we are happy about this model. Okay, then we talk about another issue, sign. The sign of the coefficient, right? Okay, the sign of price is positive. That means price and sales has a positive associationship. And here in case of ad, it is negative. The sign is negative, meaning that when the cost for ad goes up, sales goes down. Okay, so first I check one by one. Price, the sign is positive. The sign is positive means when price goes up, then sales goes up, and when the price goes down, sales goes down. But that never happen. That never happen because when price goes up, normally sales goes down, or when price goes down, normally sales goes up. So this sign should be negative, but here it has been positive. So we cannot accept the model because the sign is not proper. The sign should be negative here. Okay, then I talk about second variable. The sign is negative. Normally what happens when the producer spend money on ad, sales goes up, and when the producer spend less money on ad, sales goes down. So the sign should be positive, but here the sign has been negative. So we cannot accept the model because the sign is not proper. So these are the bad side of this model. Okay, then we talk about our residual issue, residual matter. So first I talk about whether our model has heteroscedasticity or not. That we have, and we can check it from our plotting that I did this time. Okay, I can make it small little bit. Okay, last time we did it. Can you remember last time we did it? Last time we did Z pred and Z. Okay, and this is the things of the whole things you can see from here. Just 1 minute, I am setting it properly. Setting it. Okay, so last time dependent variable is sales, right? And last time we said Z pred. Okay, here this side is the regression standard residual, and this side is the regression standard predicted value. So last time we said, can you remember? Last time we said two things. One is Z pred, right? We said last time, and also we said Z resid, huh? We said it last time. And here Z pred means predicted dependent variable, which is sales, and this one is the standard residual of the model. So that we said last time, and it is here. And this side we can call it Z resid. Z resid, that means standard residual. And this one is called Z pred. That means the predicted dependent variable, which is sales. And these all the residuals, plotting of the residuals, right? You can see plotting of the residuals. And when the plotting of residual are haphazard, that means scattered. That means one is here, 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 one is here. There is no specific direction, or when there is no specific sequence, we can say that our model do not have any heteroscedasticity. So that means our model is good because it is free from heteroscedasticity. Okay, I can explain the scatter plot in other way. So I can explain better here. Just 1 minute, I can show you. Okay, suppose here, you come here. Okay, this side is Z recit and this side is Z pred, and these are the residuals, right? Okay. Suppose when the residuals are plotting like this, such as suppose plotting like this means residuals are going down, then going up and going down, meaning that there is a specific sequence. And when there is a specific sequence, we can say that model has heteroscedasticity. Okay. Second symptom, such as suppose if the residuals are distributed like this. I am drawing the things. Meaning that they are getting bigger. You see, they are getting bigger both sides. They are getting bigger, right? From here they are getting larger. Then also we can say our model has heteroscedasticity, and that is not desirable. Also it can be like that. Suppose when the plotting is like this, that means they are going up and going down, meaning that there is a sequence. And when the residuals are plotting like this, then also we can say that our model has heteroscedasticity. But when the residuals are like this, here you can see there is no sequence, no specific direction. They are scatteredly plotted, and it is called random. So when the residuals are plotted like this, meaning that our model does not have any heteroscedasticity. That means our model is free from heteroscedasticity when the residual is plotted like this, scattered, no direction, no sequence. And so, and what about our model? We check our model, and when I check my model, you see residuals have no specific direction, so they are scattered, meaning that we do not have any heteroscedasticity. So we are happy about the model because there is no heteroscedasticity. Okay, then finally we check whether our residual is normally distributed or not. And you can remember last time we saved our residual. Last time we saved our residual as a standard residual, right? And that we can check now. Last time we saved it. Last time we saved it. Okay, and now we shall be checking whether our standard residual is normally distributed or not. Okay, how to check? I go to analyze, go to descriptive statistics and choose the explore, right? I choose it, and you can see last time we saved it standard residual, we saved it last time, right? So I take it here, and I click the plot, and here I choose histogram and normality plot with test, right? That we check from here and continue, then okay. Okay, the result is coming up gradually. Okay, the result has come up. Okay, so here you can see test of normality, right? Okay, here is, I can make it big for you. This one I can make it big. Okay, I make it big. I make it big. Cell properties, I make it 16. Okay, it has become big. Test of normality and Shapiro-Wilk. We have two tests. One is Kolmogorov, Smirnov, and Shapiro-Wilk, and it is the standard residual statistics corresponding significant value. It is the Shapiro statistics and the significant value. Okay, there are two things. One is graphical approach and one is mathematical approach, right? So I'm writing here. So there is always two things. One is graphical approach, and the second one is mathematical approach. Okay, to test anything, testing method, right? Testing method, there are two ways. One is graphical approach and two is the mathematical approach. Okay, out of these two approach, mathematical approach actually can tell you the right thing. That means mathematical result can make it confirm, whether our residual is normally distributed or not. Okay, and here you can see what is our null hypothesis. Null is residual is normally distributed. That is null hypothesis. An alternative hypothesis is residual is not normally distributed. Okay, so first we check mathematical approach, right? Mathematical approach. Then we shall check graphical approach. Okay, so we check it. Okay, there are two tests, and so this one is the mathematical approach. This one is the mathematical approach, and here the first result, columograph, the significant value is 20%, meaning that we cannot reject null hypothesis. And what is our null hypothesis? Residuals are normally distributed. Okay, then we check the second mathematical approach, Shapiro and Wilk test. The significant value is 46.6%, which is more than 5%. So we cannot reject null hypothesis, meaning that our residuals are normally distributed. So we have already taken decision our residuals are normally distributed. So we are happy about the model, because that is always desirable, that residual should be normally distributed. So we have make it confirm already, but still we can check the graphical approach, right? I go down. So the first graphical approach, that is the histogram. I make all so that you can see better. Graphical approach, you can see from here. I make it small if possible. I don't know. Okay, I can make it. Okay. This is the histogram. Make it further small, little bit small. Okay, here you can see. Okay, residuals are histogram. It is the residual, right? Standard residual, and it is the way it has been plotted. It looks like a normal distribution, right? The way it has been plotted, actually this looks like a normal distributions, meaning that our residual, standard residual, is normally distributed, and it is our graphical approach result. Okay, then we say our second approach, graphical approach result. We can check from, I make it small. Okay, graphical app result, you can see from here. Okay, it is the normal QQ plot of the standard residual, and it is the line, right? And normally we say, when this plotting, you can see the circle, when the circles are on this line, then we can say our variable, which is residual, is normally distributed. And here you can see all the circles are on this line. So we can say that our residual variable is normally distributed. Okay, so this is the second graphical approach, and we can also take one more graphical approach. Suppose box plot. I can take it box plot, right? I can make it small for you. Okay, I can make small for you, right? Okay, it is standard residual, right? Standard residual, it is here, standard residuals, right? And normal, and it is called median. This line is median. Normally, when the median is at the center, we can say that the residual is normally distributed, or our residual variable is normally distributed. Actually, what is the things normally happens? This is called median, right? If the median is close to top, meaning that our distribution, that did the plotting should be negatively skewed. When this line is close to top, then we say that distribution of the variable is negatively skewed. But when this median line is close to bottom, then we can say that the plotting should be positively skewed. That means that the distribution is positively skewed. But when the median, this line, is at the center, that means it is here, right here, then we can say that distribution is normal. Okay, so according to this result, the distribution is not normal. Actually, according to the result, it is positively skewed. But only this thing is telling positively skewed. But what about others? This one actually talking about our residual is normally distributed. This one also say residual is normally distributed, and also our mathematical approach say that distribution, the residual variable is normally distributed. So we can take a decision that our residual is normally distributed, although the box plot, this is called box plot, they say something else, but we shall not accept the result of box plot. Thank you very much for being with me. Okay, so we can for this model, we have talked about many areas, such as we have talked about R-square, we have talked about serial correlation, we have talked about heteroscedasticity, we have talked about sign of the coefficient, we have talked about heteroscedasticity, we have talked about normality of residual. But we cannot accept the model as a whole, because this model has a number of statistical problems. So we cannot accept the model. So we cannot accept this model because it has a number of weaknesses. Thank you very much for being with me for a while.